In this video, I'm going to talk about Hertzsprung-Russell diagrams. We're going to talk about how to read them, how to analyze them, and what they tell us about stars. Like normal, I'll start with some theory, and then I'll go on to do some solutions to questions. Please take a moment to read the success criteria I plan to cover. Now here's just a quick reminder about luminosity. I do have another video about luminosity as it applies to stars, but because it's on the y-axis of the Hertzsprung-Russell diagram, we kind of need to make sure we all know it. So we have L, and it's the power that the star will radiate, the total power. And you can see here that luminosity is going to equal this sigma, that's the Stefan-Boltzmann constant, times the surface area of the star, times its temperature to the power 4. So this is called the Stefan-Boltzmann equation. Temperature has to be in Kelvin, like normal, because this is not a delta T. And what we'll find is then that a star that has a higher temperature will then give off more power. Likewise, a larger star will give off more power. So what that does mean is a luminous star could be because it's either very large or it's very hot. One other thing to think about is stars with greater masses will then have a greater force of gravity pulling them together, making those particles closer and closer, which means that fusion is going to happen at a higher rate, therefore having a higher temperature. So main sequence stars then that have a larger mass, and that's the definition of massive. Massive isn't supposed to be size, it means having more mass, tend to have higher surface temperatures and brighter luminosities. So let's take a look right here. Here is our Hertzsprung-Russell diagram. Now, Hertzsprung and Russell were two scientists that worked independently. They came up with this idea of putting all the data for these stars together and found that stars tend to group together with common characteristics. So this line here we're going to call our main sequence stars. And you can also watch my other video on the nature of all of these stars are. So along here, most stars spend most of their time in this main sequence. We also have this pocket up here with the giants or the supergiants, and down here in the white dwarfs. Take a look at these axes. First of all, I have 1 over 10,000, 1 over 100, 1, 100, 10,000. So this is a logarithmic scale. It is not linear. The other thing is it says that it's in comparison to the luminosity of the sun. So if you were the luminosity of our sun, we would give you a value of 1. This one will have a luminosity 100 times greater, or this is now 100th compared to our star. So our sun would be along this line somewhere. It is a main sequence star. It's going to be in this area. Another thing, notice the temperature scale. I have 4,000 over here, but 2,500 here. It's in the opposite direction we would normally go. So these white dwarfs have a very high temperature, but a low luminosity. If we compare that to these giants right here, they have a low temperature, but a high luminosity. Here's a diagram just from another source. Notice it has spectral class here. It used to be that we ranked stars in their spectral classes, not based on their surface temperatures. Now, we don't need to know this for the IB, but I thought I would just include this here in case you see it somewhere else. So as I said, here's our main sequence star. Red giants, supergiants, again, showing that our white dwarfs down here are low luminosity, but because they're on the left, we have a high temperature. Now there's a lot of information that we can get from here. Remember this equation, the Stefan-Boltzmann equation, L equals sigma A T to the power 4. Well, we're looking at the luminosity, and we know that it's proportional to temperature to the power 4. Because this is a log-log graph, so in other words it's logarithmic in both directions, this actually will give me this straight line. Now remember, this is in solar units, so 1 would be the luminosity of our sun. I have this dotted line here. And what happens is all along this dotted line that all of the stars here would correspond to 0.1 times the radius, the circle with the dot in the middle is the sun, 0.1 times the radius of our sun. So we end up getting a straight line corresponding to stars that all have the same radius. And so this one radius of the sun is all those stars that have the same radius of our sun, which means I can do this. And I can show that the temperature is just under 6,000 Kelvin. I don't have that great of a graph here, so don't quote me on that number, but we're in the right ballpark. Note, many main sequence stars are right here along the radius of the sun, and they just tend to change above and below the middle here. And we can get other similar patterns. You can see here the sequence that our sun will be expecting to travel from a main sequence star into the red giant. It'll go up and over down here. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. So let's go through an example. I have the surface temperature of 2 stars is given to me. It's of the order 10 to the power 4 Kelvin. Notice the number right here says K times 10 to the power 3. So if I want this number, that will be 10 times 10 to the power 3. So that will be right on here. It tells me that luminosity of A is in the order of 10 times the luminosity of the sun. That will be here. This should say, well, the luminosity of B is a factor of 10,000 smaller. So if I look at B, that will be our 10 to the power 10 times 10 to the power 3 divided by 10 to the 4. I'll keep that in units of times 10 to the power 3. This is going to give me 10 to the minus 3. So my luminosity will be down here. This will be B. And so you can see I've done A part 1 and part 2. I've labeled star A in the right spot and B in the correct spot. Identify the nature of star B. Well, down in this area, this is where we said we had the white dwarf. It has a pretty high temperature and a low luminosity. Draw the evolutionary path of star A. Well, if we think of where A is starting here, the luminosity of the sun is 1, and we know that it's going to be about here in terms of its temperature. So A is going to be a main sequence star. And it's not a very high mass. So that means it's just going to become a red giant. And part of the evolution then means it's going to become a red giant and then eventually to become a white dwarf. So what's this star going to do? It's going to move off of the main sequence stars. That means it's going to go up here, and then eventually it's going to come down towards the white dwarf. I should have it peaking around 10 to the power 2 and coming down in here somewhere lower than 10 to the minus 2 for its white dwarf. Example number 2. On the Hertzsprung-Russell diagram shown, the temperature scale is incomplete. Select the row in the table with possible values for x and y. Now what they're looking for you to know is, do you know that this number has to be greater than 6,000 and this one less than 6,000? So automatically I can cut off these two. The other thing they want to check is, do you know that this should be a logarithmic scale? In other words, it should be going down by a factor. This one's going down by a factor of 10, so a log base 10, but this one might not be. Now if I had, let's just check these out. If I had 12,000 here, that would be 3,000 here. Now notice, divide by 2, divide by 2. Maybe. Let's just double check that the other one works or not. If this was 10,000, I've gone down by subtracting subtracting 4,000. And this one here, 2,000, I'm subtracting again 4,000. Well, this one is not logarithmic. This one will be. Sorry about my spelling there. Logarithmic. So that means C has to be my answer. And one more example. We've got the Hertzsprung-Russell diagram shown here. As stars burn hydrogen, they evolve, which is a possible evolutionary path of the star. So remember, this is a massive main sequence star. This would be around the size of our sun, and a small main sequence star. Well, massive ones would turn into supergiants. That's not what we have here. We don't have a letter here for a supergiant. Now, we could have a main sequence star turning into a red giant, and that's the only possible paths we have on our diagram. So we need to look for Q to R. Okay, so please read the success criteria one more time, and I hope you can say yes to all those pieces.